So, for those in computer science, we may be repeating what we did earlier the first day we met, because your colleagues in renewable we could not really meet or start the topic or the course for the semester. So we are just going to repeat just the introduction for those in renewable. So I believe most of the renewable guys will be here today. So one very important question that most of you asking yourself is that why you would have to take numerical analysis. And I believe most of you will be thinking that way, which is very, very important. So let's look at that. Now, as engineers, let's say within 2 or 3 years time, most of you will find yourself in the industry and you'll be expected to solve problems since you guys will be engineers hired for various reasons to provide expert solutions to problems in the industry. Now, these problems may bring themselves in the form of differential equations for which you guys were taught back at year 1. But however, if we should place a differential equation right now on the board for some of you guys to solve, yes, some of you will be able to solve all right, but let's say 2 or 3 years time, most of you would have forgotten and solving the differential equation will be a problem. So there was the need for us to give you another tool in which you guys will be able to solve the problem without having to go through the differential equation. And that is what numerical analysis is about. So for the course of this section, we are just going to demonstrate how this really comes out in the field of work, and just get to take an example of how we're going to solve a real life problem using the calculus approach and as well as using the numerical approximation approach, so that you get to see the difference, how this really is. This is just to give you a fair idea of what goes on in the field and how you can use numerical analysis to bypass the differential equation, which might be later be a problem in the field of work as you see it. So the objective of this whole course, that is numerical analysis, will be to provide you guys with a concrete idea of how numerical methods and how they relate to engineering field, engineering and scientific problem solving. So with this in mind, we are going to, it will be expected that at the end of the day, you should be able to apply numerical analysis or numerical methods in the field of work. Okay. And with that, we are going to look at understanding the theoretical and practical aspects of the use of numerical methods, implement numerical methods for a variety of multidisciplinary applications, establishing the limitation, advantages, and disadvantages of numerical methods in some cases. And those in computer science, if you guys remember, I told you that once it gets to the field, other engineers like those in renewable, mining, mechanical, electrical, these will be the guys implementing your softwares in which you guys are going to build. So for you, we are going to, those in computer, we are going to look at some of the theoretical and practical aspects of these methods, so that when you guys are to develop algorithms for numerical methods, you would have the understanding which is necessary for you to start with the algorithm. So you guys might be going deeper than those of in renewable. So as a prerequisite, it is assumed that you already have some background in algebra, which you were taught in year 1. Now, with a calculus, I will stay a little bit silent on this, but if you know calculus, that is going to be a plus to you, okay? But we are not really going to use calculus in here that much. And finally, you also have a little bit experience in computing. So that is also something that, okay. Benjamin Kodo is saying that you cannot really hear me. Is that the case for everyone? If that is the case, let me get some response from you. Okay, so Benjamin Kodo, okay, a lot are saying they can hear me, so you may have to, okay, you may have to up your volume or something. Okay, let me see if I can increase my volume or microphone sensitivity. Okay, hello. Okay. Just give me a second as I try to increase my microphone, if that will be possible. Okay. 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 How is it now? Okay. All right. Okay. So, Abdullah, thanks for the response. Nanaya, I think it's okay now. So we can proceed. So, yes. So once we are talking about this computing, already we have computer guys in our midst, so that wouldn't be a problem for them. However, with those in renewable, have you tried any or have you done any course relating to programming? Let me see some thumbs up if you have. Those in renewable, for computer guys, I'm not going to bother asking because that is what you guys eat for breakfast. However, those in renewable, do you guys do any or have you done any programming course since you came to this university? Okay, so Dixon is typing. Uh, Let me guess, Charles is not online. Okay, so Dixon is saying no. Ekpiatu is saying no. I see. Okay. Um. Okay. Let's not bother so much about that. But this is what you can do. I believe you are all familiar with our calculators. And as the name suggests, numerical analysis, we shall be doing a lot of numbers in this course. So make sure you have your calculators on standby because you'll be doing a lot of punching. So that is also one aspect of computing, that is using the calculators to find out some solutions. We are going to really use that. So please, wherever you've placed your calculator, go search for it. and make sure you bring it to class every day, because that will be important for this very particular course. Now, with the mode of assessment, 10% of course will be for attendance. Group homework, that will be 2, also going for 10%. The group presentation, which is an interesting section of this course, and I like that one a lot, will go for 5%. And we'll be having 2 quizzes worth 15%. And finally, your 60% end of term exams. Okay. So basically, this has been the general format for assessment in UMAT, and we are going to strictly follow the same. Now, in the case of the attendance, I shall be giving it randomly. Okay. At times, I can take it online. At times, to maybe when we come to class, I can just take that. It's just going to be random. Okay. So make sure you are present all the time. Now, if you like to contact me, you can do so with these 2 emails that we have here. But normally, I'll prefer the first one, that is the institutional mail. And already, I believe you all have this code. That is the VLE class code, numerical analysis at 21. And at 21, like for 2021. Now, for the course content, we shall be looking at Introduction to Numerical Analysis. And from there, we are going to see the various methods in numerical analysis which we could employ. So we are going to go through all that up to chapter 5. And with all these cases, we shall be looking at a way to bypass numerical, that is differential equations, which we shall experience in the field of work. So chapter 1, that is Introduction to Numerical Analysis. But before we go through with that, is there any question before we start the lecture, really start the lecture for today? Okay, so Joseph Apete, I've seen your private message, and thanks for letting me know. Okay. Okay. So I believe there's no question, then we can start off with our chapter 1. Now, for those of you in renewable, for chapter 1, we are going to look at these objectives. That is, we are going to see how numerical methods relate to engineering field of work, and how some mathematical models that can be formulated based on some principles and stimulate the behavior of simple physical systems, and understand how numerical methods afford the means to generate solutions. So we are just going to look at that. Now, with all my topics, I would like to start with the problem. And this is an activity or a sport that we would like to establish one in Ghana. Unfortunately, there isn't one in Ghana, so we are thinking of establishing this company. And this activity, as the name implies here, it has been written down here. It's called bungee jumping. Okay. Now, I believe most of you will be familiar with this activity, where a rope or a string will be tied to the foot of a jumper and the person jumps. Now, for this activity to work, a lot of engineering goes in there, because if you don't calculate the length of the rope wall based on the mass of the jumper, the velocity at which this guy is going to go, if you don't take care, a lot of accident is going to happen. So we needed expertise from all fields of engineering. So before we could do this, that was our problem. How to relate these activities so that we could come up with an efficient system to help this activity start on board. So with this, we invited a mathematician to come up with a whole formula, or let's say a relation, mathematical model, just relating everything together. and the mathematicians came in, derived their formula, and they came up with this equation 3 that we have here, which happens to be a differential equation. No, so now as an engineer, we invite you to also come on board, and once this model has been given, we expect that you can give us a relation that gives us the velocity of this jumper at any given time based on your knowledge you've acquired from your calculus. So all that we expect from you as an engineer is that from this equation 3, we would like to estimate the velocity of this jumper at any given time. Okay. Now, for those who remember your calculus, the idea here will be to integrate this equation 3 to get the velocity. Now, the problem now becomes, how do we integrate this? Of which I believe most of you would have forgotten. But however, after going through, you should get something just like one we have in equation 4. Now, trust me, before you could get to this final aspect, it's not as easy as it demands a lot of work. If I should put this on board now, most of you will get it wrong. And if we were to be in class, I would have given marks if someone could be able to get this. It's a very difficult task to do. So this becomes our final relation that relates the velocity of the jumper at any given time. Now, this gene that we see here, these parameters that we see here is the gravity, which you obviously know to be 9.81. This M is the mass of the jumper. And also this CD we have here is the drag coefficient when the person starts with a free fall. That is the drag coefficient. So with this, let's try to look at a real life example. Let's get some parameters, numbers for values for these parameters and see how they augur well in the field of work. So suppose that we take this real life example. We have a jumper with a mass of 68.1 kilograms. And this jumper leaps from that structure on top of the sky. We have to compute the velocity based on that equation that we showed for the first 12 seconds of this free fall. And the next part of this question is that we are to determine the terminal velocity that we attain for an infinitely long chord, and we are to use a drag coefficient of 0.25 kilogram per meter. So whether it's we have all the values that we need, but just that we are to estimate for the first 12 seconds of this free fall. That will be the first part of the equation. So before we can get this velocity at any time, remember which we are to estimate for the first 12 seconds. It means that we have to substitute in our values. For instance, we have our gravity to be 9.81. The mass of this jumper has been given to be 68.1. And we have the drag coefficient given to be 0.25. So all that we do is just to put them in there and we come up with our equation as we rightly have in here. So this happens to be our gravity, our mass, our drag coefficient, and the remaining continuous. Now, if we are to simplify this equation 5, that is where we place in these parameters, we are getting this final equation 6 to be our model, in which we can use in predicting the velocity of this jumper for any given time. So let's watch something here. If you like to estimate the velocity of this jumper at, let's say, at time, let's say 2 seconds, all that we do is to place t is equal to 2, okay, and that gives us the value or the velocity that we are interested in. So let's take a look at this. Suppose we like to estimate at time t is equal to 2. Our velocity at time t equals to 2 will be equal to 51.69338. Then the hyperbolic tan h 0.1897 all times 2. Remember, we are looking for at time 2 seconds. And forgive me, my writing here is very terrible because I'm using the mouse, okay? But I believe we get the point of what we are trying to calculate here. So once you estimate this, or you use your calculator to punch in this, you are going to get a value. Now, before we proceed to see the value that we are looking at, there's something you guys need to pay close attention to, okay? Anytime you are working with equations involving trig ratios like sine, cosine, tangent, or the hyperbolic functions, such as the tan, tans, cos, sines, and the others, make sure you set your calculator to radians, okay? It's very, very important, because if you should just leave it at a degree, you probably might get a different answer, okay? So on the calculator, I think that would be, you press on mode or something, or shift mode, I'm not too sure, to change that to radians, okay? So make sure you do that. So after going through this, once you enter or you compute this, you are going to get for time 2 equal to seconds to be equal to 18.729 and 2. Okay. In that same vein, because we are estimating for the first 12 seconds, it means that we may have to determine this velocity within some seconds up to about 12 seconds. So if we should do same for 4 seconds, the velocity, just as we did for 2 seconds, going through the same thing, just that we are going to make the time is equal to 4 seconds, we are going to get 33.118. In that same case, if we do for 6 seconds, we are getting 42.0762. And for 8 seconds, we are getting 46.9575. And for 10 seconds, we are getting 49.4214. For 12 seconds, 50.6175. Remember, the question was up to the first 12 seconds. So that is exactly as we have in here. Okay. So let's see how this all shows on the graph. That is when we plot the time against the velocity, how the whole system is looking like. So with this, right from the start, you could see that at time 0, velocity is equal to 0. So for this point, that is the one that we have in here. Now, when velocity is equal to 2 seconds, we are having 18. And at 2 seconds, we are having somewhere here, which is equal to 18. Okay. In that same case, 4 seconds is equal to 33. And at 6 seconds, we are having somewhere 42, somewhere here. And at 8 seconds, we are having 46.95. And at 10 seconds, we are having somewhere 49.42. And at 12 seconds, we are having somewhere here. Okay. Now, after drawing the line through, we could say so much about this curve. Now, you can see that right from the beginning, the jumper, in a way, will pick up the velocity, a steady increase in velocity. But as time goes on, you could see that this velocity will be coming to some sort of a constant, will be coming close to a stationary point. And once it gets to a level where the velocity does not increase anymore. That is where we term as the terminal velocity, which happen to be the next part of the question. Okay, so you could see right from this table that once you start solving to a certain infinity, you could see that the value that we achieved there will become 51.69. And right when we get to this point, this velocity is no more going to increase. It's going to be the same for any number of seconds that we try to calculate. Okay, so ladies and gents, this is how, when you get to the field and there is a problem, this is how we get to solve it. That is going through the numerical calculus or differential approach. So if you remember, this was our problem, which mathematicians gave this equation. However, for us to get our solution, we need to differentiate first or integrate this problem before we could get it, which we had to be equation 4. Now, because this will be a problem that's trying to integrate this, that is why numerical analysis comes in, and that is what we are going to look at the next section, how we are going to use numerical analysis to bypass how to find solutions to this problem. So before we move on to the numerical analysis, I would like to know some feedback, whether solving this example with calculus, which is not going to be the central idea of this course. This is just a demonstration for you guys to see how we use calculus in solving problems in the industry, okay? But in the way, we are going to find ways of doing away with this calculus, and I would like to see some feedback. Was this solution clear enough to everyone before we proceed on to the numerical aspect of it? Now, if it wasn't clear, I could go over again. So I would like to see some response. Okay. So Ephraim is saying no. Philip Gorova Apreku is saying not clear. Okay, Latif is saying same. Okay, then all right. So let me go over again, okay? Let me go over again. Now let's start right from where we had a problem, which is this side. Yeah, starting right from here. Okay. Now we had a problem, and with this problem, that is establishing a company, that is the bungee jumping activity in Ghana. And for this to work, we needed the services of engineers to come on board, mathematicians to give us some mathematical models, and for engineers to interpret what the mathematicians have brought out. So with this, the mathematicians started, and they came out with this equation 3 to be a model that relates the acceleration of this jumper to the entire forces acting on this jumper. And this happens to be a differential equation. So as an engineer who are just hired to also come on board, suppose that I would like you to determine the velocity of any jumper at any given time, okay, based on the model the mathematicians have come up with, which is this equation 3. For you to go through that, it means that you have to integrate this equation that we have here, that is equation 3. And now, if I should tell you guys to integrate this, that will be a whole lot of issue, okay? So because there is going to be an issue, that is why we've tried to find alternative ways. That would be the numerical analysis. But before we use this numerical approach, I'll first of all like to demonstrate how, if we were to go through with the integration, how this was going to be. Okay, so in going through the integration, which is going to take a lot of work for you to achieve, we are going to arrive at this equation 4. So after integrating this equation 3 that we have here, we are going to get equation 4, which will be an equation relating only the velocity to the other parameters of the jumper. Okay, so let's take a real example where we had values for that, for a jumper, let's say a given problem. So suppose that a student from this class who will be the jumper, weighing a mass of 68.1 kilograms, leap from this stationary point, that is the structure in which we built, and we are to calculate the velocity of this student or of this jumper for the first 12 seconds of the free fall, and we are to use a drag coefficient of 0.25 kilogram per meter. Okay, so for us to get this, all we need to do is to place in the parameters that we've been given. So for G, which is our gravity, we know to be 9.81. We've been given a mass of this jumper to be 68.1, and we've been given a drag coefficient, that is CD, to be 0.25 kilogram per meter, all from the question. So after substituting everything in there, this becomes our final model, and that is what we are going to use. So in simplifying this model, that is the equation 5, we get this equation 6, which I believe is something that we can do. Okay, now remember, this is just a demonstration of how we would have done if we were to integrate the whole equation, and that is what we are going through now. So this becomes the final model in which we are going to use for this specific jumper. So it means that for us to get the velocity of this jumper at any given time, let's say at 2 seconds, velocity at time 2 seconds will be equal to 51.693 then tan of 0.1897. And remember, we are looking at time of what, 2 seconds. Okay, and once you simplify this or you punch this in your calculator, we are going to get, I think, 18.729 and 2. Okay, now remember that when dealing with equations like this, involving hyperbolic and trigonometry ratios like the sine, the cosine, and that of the tan and hyperbolic functions just like this, always do not forget to set your calculator to radian. It's very, very important, okay? And once you do that, you are going to get the right answer, and that is if you should punch in everything correctly, okay? So always don't forget this. It's very, very important. Now, over the years, what I've seen students do is that anytime they punch in their calculators, they'll punch it in all right. But if you don't set this your calculator mode to radians, you get a different answer, which makes your answer wrong. Okay, so always remember to do that. So once we go through with this, it means that we are getting 18.72 to be our velocity at time 2 equal to what, 2 seconds. Now, in that same vein, if you would like to estimate the velocity at time 4 seconds, this implies that this will be, just as we did for the first one, 51.693 8, then tan of 0.18977, and this time our time is what, 4 seconds, which will give us somewhere like, I think, 33 point something. Okay, so from the question, it demanded that we estimate the velocity for the first 12 seconds. So it means that we would have to do this until we get to the 12th second. And once we go through that, we are going to get this nice table that we have here. Okay, so remember that at time t equal to 2 seconds, we got a velocity of this value. 4 seconds, we are getting 33.118. Now at 6, we are getting this. At 8, we are getting that up to we get to at the 12 seconds, where we are getting 50.75. Okay, so plotting this on the graph, this is basically how the whole solution looks like. So at time t equal to 0, we are having velocity equal to 0. At time t equal to 2 seconds, we are having somewhere 18. Okay, and at time equals to 4 seconds, we are having somewhere 33, which is somewhere here. And at 6 seconds, we are getting 42, which is also somewhere here. At 8 seconds, we are getting somewhere here. And at 10 seconds, we are getting somewhere here, all from the values we are having from this table. And finally, at 12 seconds, we are getting 50.61, which when we trace to the plot, we are having somewhere here. Okay, so if we draw this line through this point that we just calculated, or we just noted on this graph, you could see that right from the beginning, this jumper picks up a steady increase in velocity. However, when it gets to a certain point, you could see that this velocity is slowing down. And with this, it's going to get to a certain point where the velocity becomes constant. It's neither going to increase nor decrease. And that is where we term to be the terminal velocity. So at this point, it means that no matter the second that we go through, this velocity is just going to be constant. Okay, and that is what we presented by this infinity symbol that we have here. So it will get to a certain point in which the velocity that we estimate for this time will be the same as the next time. Okay, and that is where the terminal velocity is really about. So if we are to go through calculus in finding solution to our problem, that is how we are going to do it. But once you do get to the industry, that is always not the case, because there are some problems in which solving with calculus, or let's say trying to integrate, becomes a very difficult task. And as such, there are even cases where you may not be able to even solve at all. So in such cases, we try to go through or find another alternative using numerical solutions. And that is exactly what we are going to try out now. Now, let's see how we get to use numerical analysis to bypass this whole idea. For this numerical analysis, we are going to find solutions to this same problem, okay, using the same problem. However, this is not going to demand any form of calculus at all, okay? So let's see how this is done. Now, I believe we all do remember how to determine the gradient of a curve, okay? Now, back from, is it SHS, when you are being given a curve, let's say just like this, and you are being asked to estimate the gradient between these 2 points, right? Now, all that we try to do is to find the difference between the y-axis and that of the x-axis, and this happens to be our x2, okay? For forgive me for my writing. I'm using a mouse, so it will be a problem. And this will be y1, and this portion, let's make it our y of 2. Okay. Now, for us to get our gradients, all that we have to do is find the difference between the y and that of the x's. So this becomes y2 minus y1 all over our x2 minus our x1. Okay. And remember, this will be how to estimate our gradient, which most of us would like to represent by m. But what we should not forget is that this m is just equal to the y all over the x. Okay, that is change in y over change in x. That is dy dx. Okay, so in a way, this is how, or this is the concept we are going to use in bypassing the calculus aspect of it. Okay, now let's see something here. Remember our equation that we had here, that is the dvdt. If we are to relate this same thing to how to estimate the gradient of any given curve, our dvdt will be equal to v2 minus v1 all over t2 minus t1. Okay, so in place of this dvdt, we can just substitute this expression that we've just calculated right here. Okay, just this expression we've calculated here.
Sir.
Yes. Nanaya.
Sir, yeah, sir, please, the question, the problem we're solving.
Okay.
Yes, sir, please, the question was asking us to find for the first 12 seconds.
Yes.
And in the solution, we started from 2, went to 4, 6, 8, 10, 12.
Yes.
So when we are given such a problem, can we skip some of the seconds as you did, or we just assumed to use an interval of 2 for the time?
Yes. Thank you very much. And sorry, I did not see your chart earlier. Now, this is what happens. Anytime there is a problem like that, now in the field of work, you could assume any interval of your choice that makes sense to you. Okay. But however, when we do come to the class, because you are about a certain number and I would like you to get the same solution throughout, I'm going to restrict you as to the time interval. Okay, so I can say that I expect all of you to work in 1 second interval or 3 seconds or something like that. Okay, so for the time interval there, I'm going to specify that for you. Okay.
Okay, sir.
All right. Okay. Thank you.
You're welcome.
So let's continue. So once it comes to numerical, as I was saying, we try to just substitute everything we have in here with the dvdt. Okay, and let's see how that happens. Now, this is our dvdt, which we just approximated, which is also known to be the change in velocity over change in time. Okay, that is the calculus thing in there. Now, this V2 minus V1 is exactly as we've expressed in here. Okay, such that if we should take I is equal to 1, okay, my screen has frozen, but let's continue anyway. If we should take I is equal to 1, it means that T1 plus 1 giving us T2, okay? So this becomes T2, however, this becomes T1. So in effect, this becomes V of T2 minus V of T1 all over T2 minus 2 at T1. It's just similar to what we just calculated back here, okay? So it's the same thing. So if we are to replace this with the whole of the V dt, we are getting something just like this, okay? So remember at first there was a dv dt, just that we replaced that with this whole expression as we have in here. Now, the idea here is that we are going to find a way to estimate the current velocity, okay? And for us to do that, we try to send the previous ones back at the other side of the equal to sign. So in this case, we are going to send VTI to the other side of the equation and T2 minus T1 to also to the other side of the equation, leaving only VTI plus 2, okay? That is the VTI 1 plus 1, okay? So in doing so, we are going to get exactly as we have in equation 8, okay? So in this case, we just made this expression here the subject, that is the VTI plus 1 the subject. Now the idea why we introduced in the I was that once it comes to numerical analysis, everything in here is going to be in the form of iteration. We are going to solve from iteration 1 for several number of steps, okay? So this I that you see in there was introduced so that it could help us with iteration, so that when we are at iteration 1, I will be equal to 1, iteration 2, I will be equal to 2, and so on forth, okay? So that is what is going to happen here. But our main idea here is that at the end of the day, we try to come up with an expression such that the latest number or iteration that we are looking here will be the one at the left-hand side of the equal to sign, which we shall be estimating. And the other ones will be a certain old value of the parameter we are interested in. And remember that from here, we have a certain t minus a past t, which is also the same as what the change in time, okay, change in the t, which is exactly as we have change in the t here. And this change in t is known to be what we call as the step size. And remember the question Nana asked, that what is going to be the time interval, and that is going to be our step size here. So when I gave you that you should do or perform the analysis in 2 seconds, it means that the step size in here will be 2, okay? So for every iteration, from this iteration to the next one, the step size is going to be 2 seconds, because that is what I may require of you, okay? So we are going to have a certain old value for expression and also a step size. Now, in between this, we are going to have what we call the slope, and that is the expression that we have here, okay? So for generally, any numerical analysis or expression is going to be of this form. That is a new value, which will be equal to a certain old value plus a certain slope times a step size, as we have in this whole expression here, okay? So basically, that is what any numerical solution is going to look like, okay? So with this, let's use the same parameters as we had earlier and see how this also falls out. So using this expression that we have right here, let's try to put in the parameters that we know and see how this whole thing becomes. So because we are going to use, just as we did for the calculus 1, as we are using 2-second time interval, we are going to use the same thing here. And in that case, that becomes our step size. So for us to estimate our velocity at time equal to 2 seconds, our velocity at 2 will be equal to a pulse value of velocity. And remember that the pulse value was when this jumper was stationary. And when this jumper was stationary, the velocity 2 was equal to 0. Okay, so this becomes 0 plus our gravity, which we had here to be 9.81, minus our drag coefficient, which is equal to 0.25, all over our mass, which is 68.1. And we have the 68.1. And remember, we also have another pulse value of velocity here squared. And our pulse value was equal to 0 all squared times the step size, which is the change in t. And because we are dealing at an interval of 2 seconds, our change in time, which is our step size, will be equal to 2. Okay. Now, once we evaluate this on our calculator, we are getting 19.6 to 1 second. Okay, so let me read a question from, before I continue, let me read a question from Joel Kobe. Now, Joel is asking, randomly in question, is the step size always given? Yes, the step size will always be given. That is, if you are working in the form of a quiz or something, I would like to see the same result, so I'll restrict you to the step size, okay? But however, if one day you become your own boss in your own work and you would like to modify this step size, you can choose to do that per your own discretion, okay? Any step size that makes sense to you, you can use that. But in the case of a quiz or an assignment, I'm going to restrict you to this step size, okay? Yeah. So continuing, yeah. So once we perform this calculation, we are getting 19.62 meter per second to be the velocity at time 2 equal to 2 seconds. Now let's look at the next iteration, which in this case will be velocity at 4 seconds. Now remember that the whole idea of this expression is that for us to estimate any new value, we have to make use of a certain old value, okay? Now, because we are moving on to the 4th second, this old value is no more going to be this 0 that we have here. It's going to be the immediate past velocity, which we just calculated for the 2 seconds, okay? So this velocity will be our old value for this new velocity as we have in here, okay? So in doing so, our new velocity will be estimated as 19.62, which was the velocity at time equal to 2 seconds, plus the remaining parameters remain the same. However, this velocity that we had here also changes to the current velocity of the jumper, which was at 2 seconds, which is 19.62 all squared times the step size. And remember, because we are dealing with a step size of 2, this step size is going to remain constant throughout the whole computation, okay? And once we simplify or compute this, we are getting 36.417637 meter per second. So if we should go through this same principle until the 12th second, we are going to get something 51.6008. Okay. Now, let's see what we've done so far. We've tried to determine the solution to this problem. One, going through like calculus approach, which is called the analytical solution, and also the numerical approximation approach. Now you could see that because we are using two different methods, we are bound to get something different. Now let's look at this chart. Now this chart you see here is the plot of the solution we had when we went through the calculus, which is given at this blue line, okay? And from the one that we just estimated, that is the calculus, the numerical approximation, that is the one that we've indicated to be the black line. Okay, so as velocity times 0, velocity 2 is equal to 0. At time 2 equals to 2 seconds, we are having somewhere 19.62, and that is our 19.62. At time 4 seconds, we are having 36.41, and this is our 36.41. At 6 seconds, we are having 46.92, and that is our 46.92. And at 8 seconds, we are having 58.180, and that is exactly as we have in here. And at 10, we are having 51.31. And finally, at 12 seconds, we are having 51.660. Okay. Now, if we should compare the solutions from that of the calculus to that of the numerical approximation, you can see in that once you get to some places, we account or we see some sort of deviations in there, and that is the errors, or let's say some of the deviations that we expect to see because we are not going through the calculus approach. And remember that I told you from earlier that because we are using a different method, or let's say a bypass, we are bound to experience some deficiencies in our system. But however, what happens is that as we approach infinity, the solution converges to the same point, maybe with a difference of a very small error. So you can see from this position that the solutions here are very close. Okay, so that is one thing about numerical methods. Right from the start, you may not get the solution as you wanted, but as you perform more iterations, the solution gets closer and closer as you move on forward. Okay, so that is what numerical analysis really goes through once we talk about numerical analysis. So basically, that is the whole idea. Remember that this whole section has been how to demonstrate really what goes on in the field of work. And if you are to go through with a calculus approach, that is perfect. However, when it comes to a certain point where you seem to have forgotten your calculus, the other alternative in here will be to go through with numerical analysis. And although numerical analysis might not be perfect, but once you perform further iterations, more and more iterations, the solution get closer and closer to the value or the solution that we are interested in. Okay, so that is the whole concept of numerical analysis. And from this point forward, we are not more going to deal with calculus. We are just going to see the various forms of numerical methods available. But this is just the general form of it that we looked at. But in future, we are going to look at more of this, and that is going to be fun to look at. So this is how we go through with it. So let's see. Is there any question? Is there any question with this numerical approach, or should I go through over again? I would like to hear some feedback. So Joel is saying, okay, that was way back some time. So I'd like to see now whether this numerical approximation was okay. This would have been best if we were to be in class, but unfortunately, COVID, we would have to adjust. So that is that. Okay, so Nanayao is typing. Okay. Okay. Okay, so Nanaya is requesting that I go over. Okay, let me go over once again, okay? For the sake of those who may not be able to type, I believe some of you will be using your smartphones and typing becomes an issue in there. So let's see if I could do this again. But Ephraim Sapon is typing something. Let me see what he's typing, then I proceed with it. Okay, so Ephraim is asking the parts about approximation, are they going to be accepted as solutions? Yes. Ephraim, let me answer this. Yes, they are going to be accepted. Okay. And before they will be accepted, remember that once the initial stages, the solutions might not be perfect. Okay. But once you continue to increase the number of iterations, you get to a perfect solution. Okay, you get something closer to the exact solution in which you are wished for. Okay, so it's all about performing further iterations. Okay, until it gets to a certain point. Now, how do you know that you've gotten to, let's say, a closer, let's say, solution? And that is what we are going to look at in our next section, what we call the errors, how to estimate errors. Okay, error analysis. We are going to look at that once we get there. Okay, but ideally, once you are having a problem and you would like to go through with numerical approximation, you have to perform several iterations before you get somewhere closer to the solution. Okay, so Ephraim Sapon, I believe I've answered your question. If it's still not clear, okay. So Fatima is saying that I should go through the derivation of the numerical equation. That is no problem. I'm going to do that. Okay. All right. Okay. Thank you. So let's go through with the derivation again. So going back to where we derive this whole expression, that is right from here. Okay. Yeah. So with this, for us to bypass this calculus aspect of our equation, remember that we had a divinity. Forgive my writing. I'm just using a mouse, so it's kind of very difficult to write in here. Yeah, so we had a divinity in our equation that was derived by our mathematicians, which made it a differential equation problem for us. So let's see how we bypass this. Now, remember your equation, how to determine the gradients of a curve. So suppose that this happens to be my curve, the one that they've drawn beautifully here. Okay. And I would like to determine the gradient of these 2 points. Now, remember that for us to do that, all that we needed to do was to find the change in the y-axis, which we have here, all over the change in the x-axis. All right. But in this case, our axis here has been denoted by V and T. Okay. So for us to get this, our change in V is exactly as we see at the upper side of this equation. And our change in T is the one that has been designated down here. Okay. And this is equal to our gradient, which is our M, which we also know to be our dV or dt, which is just an approximation of dV dt. Okay, so that is what we have here, our change in t, our change in v, all over our change in what? T. Okay, so in place of our dV dt that we had in our equation, we could just replace all that using this expression that we have here. And once we do that, we are getting this expression as we have in here. So remember that at first we had the v, the t, right before this equation, which we are substituting with this whole expression that we have here, okay? So once we do that, it means that we've taken away the differential equation aspect of this whole problem. So with this becomes an expression which we can use in solving for our solution numerically, okay? Now, the idea here is that we try to estimate the current value, okay? Or should I say the future value, and send all the remaining parameters to the other side of the equation. Once I talk about the other parameters, we are looking at Vt and T1i minus Ti. We are going to send all this to the other side of the equation and leave this one here because that will be our future value that we are interested in. Okay. So once we do that, we are getting equation 8. And equation 8, we have our value, our velocity, which we would like to estimate, which will be equal to a certain velocity, which will be a past value. Remember that this is Ti, and this side will be Ti plus 1, okay? So this Ti and Ti plus 1 tells you that if this happens to be 1, this will be the next one, which will probably be, say, 2, okay? So we shall always be interested in estimating a certain future value or something like that, okay? So once this happens, this becomes our expression. And if we should look at this side of the equation, that is where we have the Ti plus 1 minus Ti. This, in effect, is the same as the change in time as we have in here, okay? So anytime a question is being given, this change in time will be specified for us to deal with. So in effect, we are having this equation 9 with everything in time, okay? So once we are talking about numerical solution, its general form will be a certain new value which we shall be interested in, which will be equal to an old value times or plus what we call a slope times a step size, which is the same as what? The change in time, okay? So when a question is given, most of these parameters can be deduced right away, which we are going to look at, okay? So taking that same example as we had from earlier, but this time we are going through with numerical approximation. So for us to get our velocity at time 2 equal to 2 seconds, and remember that we are dealing with time interval of 2 seconds each, it means that our change in t, which we have here, will be equal to 2 seconds, okay, or it will be equal to 2, okay. So for us to estimate our velocity at time 2 seconds, that is for the first 2 seconds, this will be equal to a certain old value of velocity, which we have in here, okay. So this old velocity will be deduced from when this jumper was stationary, when he had not jumped yet. And at that time, the velocity 2 was equal to 0, plus what we have here to be the g, which is the gravity, which we know to be 9.81, minus the drag coefficient of 0.25, all over the mass of 68.1, which we have in here, times velocity, which is a past velocity, which we have to be 0, okay? Because remember that when this jumper was stationary, the velocity 2 was 0, okay? All times a step size, this step size, and remember we are dealing with intervals of what, 2, so our change in time or our step size also becomes 2. Now once we simplify everything in this, we are getting 19.62 meters per second. Now let's try to do same for the next interval, or let's say the next iteration, that is from 2 seconds to 4 seconds. So in doing so, this becomes velocity at time 4 seconds, which will be equal to ascertain the immediate past value, or should I say the current value of velocity, which we just estimated when the time was equal to 2 seconds. And remember, this time we are no more going to use 0 because 0 is like past velocity. But remember, we are going to use the immediate velocity which we just calculate, okay, or the immediate parameter we are interested in. So in this case, this is going to be 19.62 plus the other parameters which remain constant. However, this velocity in here is going to change because we are going to use the immediate one. We are no more going to use this 0 again. So everything is like carry forward. Once we move forward to the next iteration, we use the immediate past values. Okay, so this is what is happening in here. So once we go through with this, we get 36.4136. And remember, the step size also remains the same because from 2 seconds to 4 seconds is also 2 second time interval. So that will be the step size we use for the whole thing. Now, in that same case, if we were to estimate the velocity at 6 seconds, in this case, the velocity for that is no more going to be this. We are just going to use the 36.416 to estimate that of velocity at time 6 seconds. And we are going to proceed until we get to the next one, okay? So in doing so, up to the last portion, we are going to go through until we get to the 12 second, which was demanded by the question. And that is what we have to be the 61.6008 as we see in here, okay? So in comparing the results that we had, that was from the calculus approach and that of the numerical approximation. The calculus approach is the one that have been given in this blue line, that is this curve, okay? And the one in the numerical approximation, that is this solution, that is the one that have been plotted in the black line. So when time at 2 seconds, we had velocity at 19.62, which is the one that we have in here. At time 4 seconds, we are having 36.41, which is what we have in here. At time equal to 8 seconds, we are having 46, which is the one we have here. At 8 seconds, we are having 50, and that is that. And at 10, we are having 51. And finally, at 12 seconds, we are having that, okay? So you could see right here that because we are going with numerical approximation, we are bound to encounter some sort of deviations, okay? So you can see right from this point, there's some deviations in there, okay? Deviations in there and that, okay? So these are some of the errors or deficiencies with numerical approximations. You do not get the solution straightforward. However, once you begin to perform more and more iterations, you can see that the solution is getting closer to the exact solution, okay? So in reality, if you should have any numerical problem, for you to get a more definite or a closer solution, you would have to perform more iterations, okay? So let's say the thing to note here is that if you have a problem and you can solve with calculus or differential equations, go through with that. However, if calculus or your differential equation is not in good standing at that particular time, you can go through with numerical solutions, and that is going to give you something really close to the answer, okay? And that is also something that you guys needs to be aware of, okay? So once you go through numerical, you're going to get some deficiency. You might not get the solution exactly as you want it, but once you perform more, you are bound to get something much more concrete. than this one. Okay. So I believe this will be clearer now. But however, for those of us who are not so clear, you can visit me later in the office and we can go through. And I'm going to see if I can rehash this when we get to class. That will be much more appealing. Okay. So basically, that is the whole idea. Remember, this is just a demonstration to see how numerical analysis differ from that of what differential equation, how to estimate the analytical solution for any given problem. Okay. Yeah. So I could see that Abdallah, okay. Abdallah is saying that we are okay. Okay, so that would be great. So the question is now becomes, if you go to the industry, and remember the industry is much particular about getting their answers right. So this implies that for you to get an accurate answer, it means that you have to perform several thousands of iterations. Okay. Now let's see what is happening here. If you are to solve this same problem for about, say, the next 1,000 seconds, just imagine the kind of work that we are going to do here. Practically, although we are going to do it, but it's going to take some time, but practically is, let's say, a waste of resource because it's going to take us so much time for us to get to do this. So for this reason, numerical solutions or numerical approximation, most of them has been turned, or this kind of work is being given to computers for them to do. So algorithms have been written down just to perform this kind of task. Okay. Now talking about algorithms, computer science and engineering students, they do know their softwares, their programming languages, the Python, the C Sharp, the C plus, the MATLABs and the others. They're all there available for this kind of computations. However, for those of us, I mean those in renewable who are not so much into programming, basic softwares that we could think of will be the Excels and the others, which we could also use. Okay, so softwares like Excel, MATLAB, Mathematica, Maple, all could be used in solving these kind of problems. And as a demonstration, we are just going to look at how Excel will be used in, let's say, achieving all this stuff. Okay, I believe for Excel, there we are all familiar with it because right from year one, that is introduction to computing, you guys were taught a little bit about Excel. So it's fair to say that we all know Excel and how to use it. Okay, so let's see how we are going to do this using our Excel. So in launching my Excel, yeah, yeah, yeah. So let me just launch my Excel. Yeah. So Excel has been launched. Okay. So now let's see what happens in here. Okay, so Excel. Yeah. Yeah. But before that, let me see by hands. How many of you here are familiar with Excel? How many of us are familiar with Excel? Okay. All right. Okay. So you have some takers. Okay. So that is great. Nice. So let's see how we get to do this with our Excel. Now let me increase the size a little bit so that you could all see. Great. So for this to work, let me just copy my problem here. Okay. Yeah. Let me copy the problem here. Okay. So let's take that. Yeah. So let me just paste this somewhere here. Okay. So that will be our equation. I'm just going to put this here so that you see exactly what I'm typing. Okay, after I say that we cannot see, let me share my screen again. Yeah. Okay. How is it now? So, okay, give me a moment. Okay. Okay, I believe now it will be okay. You cannot see, yeah. Okay, yeah. So this is okay. So going back to the Excel. Yeah, so this is it. So let's see how we get to solve this. Now, remember that we are trying to estimate velocity with some time. So let me call this first cell the time, which is in seconds. Now let me make this a little bit bigger and bolder. Let me keep this up. Yeah, that. And for the next column, the parameter I'm interested in, that is the velocity, also in meters per second, okay, which is also here. Now, at time 0, we need to estimate our velocity for that. Let me, okay, yeah, so that is our expression. So for us to get our velocity, you can think of, let's say, coming up with a formula that is typing in this formula into our equation, into Excel, so that we are just going to just generate the solution. So for those in computer science, I think this will be something easier to do. And for renewable, I don't think this is so complex. You can easily punch this on your calculator for the calculator to do this computation for you. It's no big deal. Okay. So with this, in typing my formula, this will be equal to yeah. Oh, what is happening to my keypad? Yeah. So this will be equal to 51.6938 times the hyperbolic of that. Okay, so that will be tan h into bracket 0.18977 times the time, which we have to be the score. And once we do that, we are getting this number. Now, suppose that I would like to go with, let's go with our 2 seconds and stuff, okay? And let's do so for about the next, let's say, 18 seconds. With this, we can just drag it down, and this is just going to give us our numbers, okay? Let me try to reduce the number of decimal places. And with the number of decimal places, I'm going to restrict to, if I want everything in 4 decimal places, everyone will have to use 4 decimal places in that regard, okay? And at times too, I can modify it as and when the question demands, okay? So this velocity we have here, remember this equals the analytical solution, that is the calculus one. Analytical or solution, that is the calculus one. Now let's see how we get through with that of the calculus 1, 2. Just put this thing up. The analytical solution. Yeah, let's get this here. Now let's do same for the velocity. That is in this case, we'll be using the numerical approach. Let me just try this. So we call this numerical. We are using numerical approach for this. With this, let me just copy the function in the meantime. Okay. Let me just get the expression here. Let me just copy any of this for now. Let me just place this thing here. Okay, so something just like this. Okay, so remember, when the velocity was equal to 0, we had our initial to be equal to 0 already. So at time 2 seconds, the velocity, remember, is equal to a past value velocity, okay, which in this case is our past one, as we see in here. So plus into bracket, we have 9.81, which was our gravity, minus into bracket 0.25, all divided by the mass, which is 68.1, bracket close, and all this is being multiplied by the square of the past value, okay? So don't forget that. Then everything closes. Then finally, we have the change, that is the step size, which was equal to 2. So once we do hit enter, this is what we are getting. And one thing about Excel is that it has a way of, let's say, adjusting itself dynamically to what you are interested in. So once we've been able to write out this program in a dynamic form, it's just going to adjust itself as to how we need it. So with this one, if we should drag for the next one, this is going to take the velocity from the immediate past value. It's no more going to stay on the first one. Okay, so this is just going to happen until it gets to the last portion here. So we can just drag this through up to this point. So you can see right from here, we are done with the two stuff. That is the calculus approach, that is an analytical solution, and we've done same for the numerical solution. Now let's plot the two so that we get to see really what is going on. So let me just select these two and just let me just select everything here and try plotting this. Yeah. So once we do that, this is what we see. Okay. So just as we had in our PowerPoint presentation, we are having something. Okay, so Marshall was saying that he's not hearing anything. Is that true for everyone, or is just the case of Marshall? Okay, you can hear. Okay, then that's it. So let's proceed. So just as we saw in our presentation, the velocity, that is the analytical solution from the calculus, and the velocity, the orange one is the numerical approximation. So just as we saw earlier, you could see these deviations right from the beginning here, okay? But as you move on forward, the solution becomes virtually like the same, okay? And that is exactly as we see in here. See that R comes closer and closer. So in a case where we like to estimate for, let's say, several number of seconds, several iterations, maybe we like to go up to somewhere 322, okay? With the use of softwares and computers just like this, we should be able to get through that, okay? So basically, that is what happens. That is why softwares are now being developed just to perform this task. And that is why, as computer science and engineering students, you guys would have to pay close attention, because you guys will be developing the algorithms for us engineers to use, okay? So if you get your algorithm wrong, it means that the engineers on the field will also get wrong solutions. And if that happens, a lot of damages will be caused, life could be lost, and a lot of money too could be lost in that regard. So for computer science and engineering students, you guys will need to understand the core concept to be able to develop algorithms for numerical approximations, okay? So you guys will have to take this course really serious. And for renewable, you guys will have to also understand the framework of numerical approximation, so that you guys will also make sound judgments and solutions.
Sir, please, there's a question on board.
Sound judgment from the analysis and everything. Oh, okay, let me just look at that. Okay, so Emmanuel Niayite is asking, why did you use analytical velocities in calculating numerical velocities? Oh, okay. Now, let me answer this. Okay, watch it. We did not use analytical velocities in estimating numerical velocities. Now, oh, sorry. Yeah. there's a problem with this algorithm. Yeah, that is a very good observation. That will be Emmanuel Nitego. Yeah. I made an error here. Now we will be using the past one, which is not this one. So we'll be using the one earlier, which is the one before. Sorry. I did not see that. Yeah. So this is okay. Yeah. So if first change this. Yeah. So for computer guy, okay, that is a very good observation, and thanks for drawing my attention. That is what we just did. Okay. Yeah. Okay. Nia is saying that the sound is cutting us in the sense that my sound is breaking up or something. Is that yes, of course, you would have to use previous numerical velocities. Yeah, you have to use that, okay? You have to use that. And thanks for drawing my attention, Ni. Ni, are you in computer science? Okay. No wonder. That is why. Yeah, that is true. Sorry for. All right. Let's wrap up. Okay, we are nearly about finishing. So yes. So always, once you are dealing with numerical, always go with numerical approximation because analytical velocities not even come into the picture. So always with numerical. So this brings us to our demonstration of how to interpret this. So in future, when you get to the industry and you are presenting your reports just like this, you are not going to report on these numbers. You are going to just report on this graph, and you do your discussion. Everything will be based on this graph. Okay. So in the future, suppose that I hire you as part of the engineers who work on this our bungee jumping project. It means that in the boardroom, I would expect to see a graph just like this, and you are going to discuss this graph. That if a jumper should start from this point, he's going to pick up the velocity that is increased, but with time, the velocity will become constant and will become stable, and that is where the terminal velocity is. Okay, so that is how you guys will be doing your boardroom discussions and stuff. Okay, and that is why. And also, we've talked about the need for softwares to be doing this kind of approximation because you might be needing so many iterations and so many points to work with. Computers have been designed to do this kind of work, okay? And that is why we do that. Now, someone will be asking if computers are there to do this kind of work, why do we have to bother ourselves learning these whole methods and everything in theory? And that is a very important question, which we are going to talk about the next time we meet in class. Okay. So until then, we are going to attend this meeting to for renewable. I think yours will be tomorrow. We are going to meet at 6 a.m. in the School of Petroleum Experts. I think that would be, is it LH9 or something, that classroom there. We are going to meet there. We are going to discuss about it. However, before we close, is there any question for me to answer before we close for the day? Is there any question? Is there any questions so that we draw the curtain for the day? Okay, Joel is saying no. Okay, Clement is saying no. So on that note, I'll see you guys. That'll be tomorrow. And for computer science, I'll see you guys on Wednesday. So until then, enjoy the week, and hope it becomes as interesting as you expect it to be. So thank you so much for attending this class, and I'll see you guys on campus. Right? So enjoy the rest of the day.